Okay. Really sorry, I don't think my slides are advancing, so I'll just go through it like this, I guess. My name's Niall Holmes. I'm a postdoc at the University of Nottingham, and Mike Packer will speak after me. I'm going to talk about electromagnetic coil systems for wearable magnetoencephalography, and Mike's then going to talk about magnetic field design in a magnetically shielded cylinder. So the outline of my talk, I'll start by talking about magnetoencephalography and optically pumped magnetometers. I then talk about some biplanar coils that are designed for field cancellation within a shielded room that enables subject movement in MEG. I'll then talk through the design theory, the uniform field and field gradient designs, the coil performance, and an example of a fun neuroscientific experiment. I'll then talk about some issues we came across and future directions that will hopefully lead nicely into Mike. So just a bit of an overview, Nottingham is there in the UK. It's where obviously Robin Hood is famously from, and I work at the Sir Peter Mansfield Imaging Centre, which is named for Sir Peter Mansfield, who invented MRI in the sort of 1980s. Obviously, Peter Mansfield and Paul Lauterbur won the Nobel Prize for their development of MRI, and key to Mansfield's awarding of the Nobel Prize was his development of magnetically shielded gradient coils that were used to reduce the acquisition time of an MRI image from sort of 10 or 20 minutes down to milliseconds. That enabled functional magnetic resonance imaging. So magnetoencephalography is the detection of magnetic fields outside the head that are generated by neuronal current flow inside the brain. And with this, you can get a very high spatial and very high temporal resolution of the underlying neuronal activity of the brain. And that's really important for understanding things like mental health and also conditions such as epilepsy and dementia and autism. The current state of the art for an MEG system is a superconducting quantum interference device, so a squid magnetometer. These are obviously very highly sensitive, sort of less than a femtotesla per square root hertz typically. They have a very high bandwidth and they have whole head coverage, so we have upwards of about 300 channels. They're also well characterized, and you get systems that look a bit like this. You have a dewar of liquid helium which contains the squid, and you put your head inside, and then we can do recordings. There are issues with squid-based MEG, is that the distance from the scalp to the coils is quite large, and as the signals decay with a 1/r cubed, we have a low signal to noise ratio. There's also a fixed sensor locations. This means we have a one-size-fits-all helmet, which makes that source to sensor distance even larger in children, meaning that it's difficult to scan them and understand the brain in the developing adult. It also means you need to keep still, and that makes it challenging to scan children and adults that have movement disorders, so such as those with Parkinson's disease or maybe someone with Tourette's syndrome. There's also cryogenic cooling involved, which means there's often high running costs. So whilst MEG is a very good technique, it can be difficult to actually address the neuroscientific questions we want to see. So this is where emerging technologies could maybe help us. So with optically pumped magnetometers, the recent commercialization of these devices means that we have sort of small, compact, self-contained systems where we have a laser source. A laser source passes through a vapor cell containing an alkali metal atom. It optically pumps the alkali metal into a magnetically sensitive state, and through modulation of the field in a desired direction, we can measure the magnetic field experienced by the cell by locking in on the modulation frequency on a photodetector. The sensitivity of these systems is pretty good. It's about 1 to 100 femtotesla per square root hertz. The magnitude of the activity generated by the brain is around 10 femtotesla to 1,000 femtotesla on the scalp, so that's bang on what we need. There's about an 150 hertz bandwidth, which is also useful for assessing about 90% of the brain activity that we're interested in. Not much goes on in the brain higher than that. We're restricted by the number of channel counts to about 50 sensors, but an advantage we get is that the distance between the scalp and the sensor is reduced from sort of 2 or 4 centimeters to about 5 millimeters. We can have a flexible arrangement of sensors, so we can put them on children, we can put them on adults, we can put them on someone whilst they wear a virtual reality goggles, we can put them on someone whilst they move around. And it allows us to just address questions that we couldn't do with the sort of old style bulky scanner that we can do with the new style kind of wearable system. So this is our development in Nottingham. For the last sort of 4 years, we've been developing an OPM-based MEG system in collaboration with University College London, and we've combined these Q-spin OPMs with 3D printed helmets to hold the sensors in place, and so that we know exactly where the sensors are with respect to the brain. So when we do our source modeling, we can figure out where the currents are flowing in the brain. And we combine that with a magnetically shielded room to shield the system from external interference, but also to allow the OPMs to operate in their spin exchange relaxation-free regime. There is then a movement problems. This was one of the first sort of things we had to address, in that when you move, when the person wearing the helmet moves, so in this example they were just nodding their head, and we recorded the motion in red for when the nulling was off, then we get this problem where the output of our OPMs clip when it reaches the sort of height of the movement. That's because of the remnant field inside the magnetically screened room. So this data down here was mapped in a vacuum schmelz AK3B. We have about 22 nanotesla of remnant field with about a 10 nanotesla per meter gradient. So that meant that even like a 2 or 3 degree rotation, or like a 2 centimeter, 4 centimeter movement here was enough to clip the output of our OPMs. So what we decided we needed to do was to compensate the remnant field inside the shielded room by developing an electromagnetic coil system, which allowed easy access to the subject. So you could imagine just putting Helmholtz coils around some sort of cage, but we want to be able to get in and out. We want the person inside the experiment to feel comfortable, and we went for a sort of biplanar coil system, designed the coils using harmonic minimization, and as mentioned before, in Nottingham there's some great expertise in MRI gradient coil design, so we adapted a MRI gradient coil design method to do this. So harmonic minimization looks at the magnetic vector. We start with the magnetic vector potential that's generated by current density, which can be described as so. If we confine the current density to the XY plane, where on this diagram over here, the XY plane is the planes of the boards, and Z is the direction between the coils, then we take the 2D Fourier transform of the current density and do Green's function expansion of this 1/r term here, and rewrite the vector potential in terms of the 2D Fourier transform of the current density. We can then further describe the surface current density by a scalar stream function, as so. And then that means we can express the Fourier transform of the current density in terms of this scalar stream function, or the Fourier transform of the scalar stream function, which means we can rewrite the vector potential in terms of this stream function S. If we then sum the vector potential that's generated by the coils at the 2 positions, so if we have Z equals 0 in the middle, one coil at plus A, one coil at minus A, we can obtain an expression for the Fourier transform of the magnetic field at a point between the 2 planes in terms of the stream function. And these terms depend on whether or not you want the same or opposing current flow on each plane. We then parameterize the stream function as a 2-dimensional Fourier series. So as 2-dimensional Fourier series of sine and cosine terms with weights alpha, beta, gamma, and delta. But then we can simplify that 2-dimensional Fourier series depending on what we expect the stream function of our final coil to be. So if you think about an example for a VZ coil, so generating a field between the planes, it's like the case of a Helmholtz coil where you'd have 2 loops of wire, which would be symmetric because they're circles, symmetric in X and Y, and they'd also carry the same current because they're symmetric in Z. If they're symmetric in X and Y, we can bin the asymmetric sign terms in our stream function, and we can reduce our stream function parameterization to a single value described by a single weight. So we can combine the weights alpha and gamma here, and combine, just multiply these two together to get a single weight for the stream function. We then simulate the magnetic field that's produced by a unit weighting of each stream function component over a series of target points that are chosen, to be within the volume that's contained by our two planes. And then we optimize the stream function by finding weights to the Fourier series which minimize the following functional. So here we want to minimize the deviation of the sum of squares of the target field at a point Ri inside the two planes, and the magnetic field generated by the coil at Ri. And this is weighted then by the lambda term for all the weights in the stream function. This final term is a tunable power dissipation term, which simplifies the final design. So a small value of omega gives us intricate wire paths with good homogeneity, as this dominates the minimization, and a large value of omega reduces the homogeneity as this starts to dominate the minimization, but it leaves simpler wire paths. So we perform this minimization by casting df by d lambda, so where lambda is the weights of the stream function, as a series of simultaneous equations, and just invert a matrix that we find. We then find wire paths by taking contours of the optimized stream function. So here are some coil designs. So these were optimized to generate homogeneous fields and field gradients over a 40 by 40 by 40 centimeter cube volume at the middle of the two coils. The coils themselves are about 1.6 meter square side length with a separation of 1.5 meters. So this is the optimized stream function for the BX coil, and then if we take contours of it and scale it to the correct diameter, we end up with wire paths where red and blue denote opposing directions of current flow. This then shows contours of the field simulated with the Biot-Savart law of the discretized wire paths that show us a good deviation. It's normalized to the field at the center of the coil, so we get about 5% error over this quite large volume. This is the example for the BZ coil. You see we get similar sort of wire path from stream function, and then we get the contours like that. The BY coil is a 90-degree rotation of the BX coil. For the field gradient coils, we see for the sort of dBz by dZ coil here that we have very similar looking wire path to the BZ coil. It's just because we've changed the current flow on the second plane to make a gradient, and the same for the dBx by dZ coil. Again, the dBy by dZ is a 90-degree rotation. This is another longitudinal gradient coil, dBy by dy, and then another transverse component, dBx by dy here. So we constructed all of these coils by mounting, we got two large wooden boards, printed out the wire paths on large sheets of A3, A0 paper, wallpapered them to the boards, and then laid the wire held in place with masking tape. And then we finished one layer and layered the second coil, layered the third coil, layered the fourth coil, layered the fifth coil. And this is how it looks set up. So we have our subject in the middle wearing the MEG system, and she's sat here in between the two coils where the field's controlled. To control the field, we use a reference array. So we have an array of OPMs that are separated in DZ, and they estimate the background field and the gradient values that are present in the room. We then feed currents through PID controllers to drive the sensor measurements to zero. Once the sensor measurements are zero, we think we've got low enough field in order to do our experiments. To validate what was going on, we mapped the field in the room before and after the nulling. So here we've got the BX field before the nulling. You see we've got about 20 nanotesla, and then about 7 nanoteslas in BY, and about 18 nanoteslas in BZ. After the mapping, we reduced the magnitude of the field from 28 nanotesla to about 750 picotesla over the full volume, which is about a reduction factor by 838. And that gives us a really good magnetically quiet environment to start doing our experiments. We looked at dynamic compensation. So, firstly, I guess, so we went from this system of sort of a coil for every single component, but if we remember that the difference really between the BZ and the dBz by dZ coil is that we reverse the current on one plane, and the same thing happens for the BX and dBx by dZ coil, we can actually rewrite our minimization to co-optimize designs to generate these balanced coils, which simultaneously can produce a good field and a good gradient, meaning you only need to construct 3 coils instead of 6. Each coil, each plane then has a individual current supply, but you don't need to construct as many actual windings. We also looked at dynamic compensation. So this is data taken in London, where we put some coils into an MEG system in UCL that was very close to the London Underground train line. So the London Underground is quite regular. It runs about, you have trains every sort of 2 or 3 minutes, so you can't even get through a 10-minute scan without having about 10 trains running. And you can see the sort of artifacts that they're generating are quite large, and obviously that would mask the brain activity that we're trying to find. So we looked at a sort of high-speed feedback loop to try and constantly null that field, and it flattens it out really well, does a good job of not showing the artifacts from the trains. We get about 40 dBs of shielding at 0.01 hertz, and it with diminishing returns after about 1 hertz, but most of the artifact is this low frequency stuff. We've since taken these coils that we designed for MEG, and we've licensed the technology to Magnetic Shields Limited, who are a company in England that make magnetically shielded rooms and other mu metal components for things. They're available to purchase to help other labs that want to set up OPMs for MEG, to help them set up these systems. So that's great for us. This is just a quick example of an experiment that you can do. You've got, we wanted to show something that you couldn't do in a conventional scanner. So you imagine getting into an MRI scanner, you're in a enclosed environment. If you get into an X-ray CT machine, it's all quite enclosed. You can't really do natural tasks. And this is bad, not just because you can't scan the populations that you're interested in, but also because you can't do neuroscientific experiments that are actually, exciting. Like, we want to see what the brain's doing when it's just in its normal state. It's quite an unnatural state to go into one of these machines and just press a button every time you see something flash up on a screen. But in this case, we were able to have one of my colleagues was sat playing, ping pong, just bouncing a ball on a bat and then resting the bat on her knee. And we repeated this a few times, and we managed to localize the brain activity, so the part of her brain that controls her hand movements, so the motor cortex. And if we look at the temporal variation of the signal, we can see a decrease in the oscillatory power of the brain over that region during the time that she's moving, and a subsequent rebound as the brain gets back to a normal state once she's stopped moving. So this was really exciting for us, and it shows that we can move on and do really cool experiments. So we're starting to think about things in virtual reality, scanning children, scanning Tourette's patients, and hopefully lots more cool things. One thing to note is probably slightly naively, we designed the coils assuming that they operated in air, but obviously, as has been mentioned before, today the materials used in the construction of the MSR have a very high magnetic permeability. This obviously distorts the shape and the homogeneity of the magnetic fields that are produced by the coils, so that our measured results are not accurate to what we simulated it for. We've already heard about the method of mirror images in order to model these interactions, and Mike's going to talk about incorporating those effects into a similar coil design for a cylindrical system inside a magnetically shielded cylinder. We also have an issue that the volume over which we can achieve good cancellation is limited to the center of the coils, and what that does is it restricts the experiments that we can perform. So although we can move around, we can only move around in a very narrow area. If we want to look at how people interact with each other, we might need 2 people and need to screen at 2 positions. If we want to look at how people interact by moving around the room, then we might need to have a wider volume where we can cancel the fields. So in order to do this, we're looking at multi-coil systems. So instead of designing a distinct wire path that generates a field, we're looking at making systems that are comprised of multiple unit coils with simpler wire paths. And then we can optimize the current supplied to each coil in order to synthesize current densities which produce sort of arbitrary magnetic fields at user-defined locations, and that should make it easier for us to adapt to, different subjects, different patient populations, and different neuroscientific experiment requirements. And it could also operate in a data-driven way that automatically incorporates these interactions as they manifest themselves. It takes the difficulty out of the modeling and out of the accurate discretization of wire paths and just puts it all into the complexity of the control system. So we're working on a prototype system. So this is an example prototype 48 channel system that was designed to be similar to our biplanar system so that we could evaluate the performance. But then it could easily be expanded to something that could be put into a room where we could look at different, just look at hiding the coils as much as possible. So in conclusion, the use of these active magnetic shielding systems has been crucial to the development of OPM-MEG, and it allows wearable brain technology to become a reality. And we're hoping to keep on pushing this and do some really exciting neuroscientific stuff. Future developments in coil technology is what's going to drive that, and it will allow for accessing subject groups and experiments that are inaccessible with the current equipment. So thank you for listening. I'm very sorry about my slides wouldn't advance at the start of the talk. And well, I'll take some questions if there are any, and then hand over to Mike, who will talk through the rest of the talk. So thank you.
I have a question. What frequency did you try to correct for your field correction algorithm?
It's low pass filtered from like 2 hertz, I think, so nothing higher than 2 hertz.
What kind of spatial resolution do you get with this technology?
With MEG, you tend to get it depends a lot on the experiment that you're doing, but we think about sort of 5 millimeters to a centimeter of resolution is achievable. With higher density arrays that are closer to the skull, you should be able to do much better. But at the moment, we're sort of limited by the size of the Q-spin devices and how close you can pack them without getting crosstalk issues.
Thank you.
Thank you.
Hi, Neil. Thanks for the nice talk. So I like this idea of this simpler grid system. So have you done any simulations yet? How dense grid do you need to be able to kind of simulate the good enough surface current densities, so to say?
I think it obviously depends on the proximity of the volume you want to generate the field over to the surface, to the coils. So the closer you are to the coils, the more current you'll require to generate a homogeneous field, and you end up with sort of unphysical. Of course, you have to do some sort of minimization to find out what those coils are. But we think with that system, we should be able to generate fields in a quite large volumes. I think if just comparing it to the biplanars, we should be able to get close to 50 or 60 centimeter cubed square side lengths from the same sort of separation. So
very nice. I look forward to hear more from that.
Cheers. Thank you.
Thanks.